So now we want to start a new topic of planar graph. So far we have learned about graph, and we define graph as a tuple of vertex set and edge set, where edge set consists of the pair of the vertices. But most of the time when we want to describe some graph, how we do it. One of the popular way that we use is we just draw the graph on a paper or board like this. We put the dots to describe the vertex, and we draw a line or more generally a curve between them to represent edges. For example, this is K5, the complete graph on 5 vertices. Yeah. So this is the drawing. But, okay, intuitively, if we see it, we know that this is a drawing. But what is actually a drawing in mathematical sense? Can we define what drawing means in a mathematical way? The drawing of the multigraph, we can also draw multigraph by adding multi-branches or loop. This is what we draw a graph on a surface. This paper or board is a surface, some type of surface. Even if, you don't have a flat surface, say you have a sphere, you can draw a graph on the sphere. So as long as it is surface, we can draw it. And that maps the vertices into points. And the edges, then maps the edges into continuous curve. On the surface. And those continuous curve has to connect the endpoints. So let's just write preserving the incidence relation. If E is like UV between U and V, then on this drawing, we have this point, which is image of this vertex U, and this point, which is image of this vertex V, and that should be mapped into the continuous curve, which is incident to both of them. So it starts at here and it ends at here. So once it is drawn, now, this vertices and edges have some physical, geometrical meaning. So this is a curve which consists of the points on this surface, and that has geometry. And, okay. So again, this drawing contains the full information about the graph. We'll see all the vertices, and then we know which vertices are adjacent and which are not. So we might as well consider this as a graph. Here it carries the full information, and then all the incident relation and adjacent relations are there. So we can just say that these points are the vertices and these curves are edges. And we will study about this drawing. And when we deal with this kind of drawing, we want to, if there is some good property that we can assume, that we want to assume it at first. And one of them is that if you think about it, we are interested in the combinatorial property of this graph and combinatorial property of this drawing. So for us, I mean, if we draw this edge between these two vertices in this way, or in this way, or in this way, makes very little difference. Especially, I mean, if you have, I mean, on this drawing, say, if we draw this curve, this edge in this way, then, I mean, somehow, I mean, before this edge and this edge does not intersect, but now this and this intersect. So this makes some difference. But as long as we slightly change it so that the, I mean, intersection relation between other objects and this curve, this edge has not changed, then it makes no difference in terms of combinatorial information. So this slight altering does not really matter. I mean, we can assume some good property. Say by moving edges slightly. So one of them is that we may assume that those three edges share an internal point. So if we have this picture, then by moving it slightly, we can just draw it this way. And also, no edge has any vertex as an internal point. So in this drawing, I mean, we can immediately identify the vertices, right? And okay, not immediately identify because, I mean, this could have been vertex, this could have been vertices, I mean, from just the drawing. But what I wanted to say was that if this is the vertex and these are the, I mean, edges, then we, by assuming this, so if there is an edge here between U and V, and in this drawing, it's difficult to, this is WSA. Then in this case, and then there is a case that there is H between U and W, and there is H between W and V and others. These two are like indistinguishable. Just seeing from this picture, it's confusing whether there is a one H between U and V or two H's between U and W and V. So in order to avoid that confusion, in the first case, we slightly move this edges so that we instead draw in this way so that to make it clear that this is edge between U and V. So that's possible. And no two edges are tangent. We can open that. If there are two tangent edges, you slightly move them, and they are either like apart or this way. So both doesn't matter. Also, we can assume that the two incident edges cross. Meaning that if you have a vertex here, and you have edge, and you have another edge, Then what? If sets and if sets intersect at the internal point. But what we can do instead is that you draw the first sets in this way, and then second sets in this way instead, so that this red curve is very close to this black one, but not really intersecting with the black, and then this green one is also very close to this black part, but not really intersect. And we can untangle this so that they don't intersect anymore. So we assume this. So to make our discussion more convenient, and then we don't want to consider all these weird cases. I mean, then they make the discussion more complicated. So we assume that from now on, we assume that the drawings that we are discussing all satisfy this good property. Okay. And okay, I just said the cross here, which was not really well-defined term. We didn't really define what crossing means, but intuitively we know. Here it was crossing two edges. They are intersecting at the internal point. But let's define what it is. In the drawing of a multigraph, crossing of two edges is a common internal point. And we say on embedding of a multigraph is a drawing which contains no crossing. And if a multigraph that has embedding in the plane is R2, which we say that this is planar vertical. And a particular embedding of such a graph into plane of multigraph is called a plane multigraph. For example, if you consider K3, you can draw K3 on a plane without any crossing. So this is planar. And there are many ways to draw it. So this is a plane graph. So this graph, K3 is planar graph, but the way how we draw each of them is plane graph. And these two are different plane graph. They are representing the same planar graph, which is K3, but they are different plane graph. The plane graph comes with embedding. So what we are interested in is the question that what graphs are or what multigraphs are planar. So that's the very natural question, right? In the following 2-3 lectures, or maybe 3-4 lectures, I mean 2 or 3 lectures are about answering this question. Okay, so in order for that, we want to first collect some properties of this planar graph. And when we are asked about this kind of question, what graphs are planar, then what's the first natural thing that we should do? We should find some examples which are planar graph and which are not planar graph. And in this case, finding some examples of non-planar graph makes more sense. And if we check certain graph, then we can check the following. The K5 and K33 are actually not planar graph. So we can prove it. So how do you prove it? One of the common property of these two is that both of them have the Hamilton cycle. The cycle that spans over the vertices. So we consider a drawing of either K5 or K33 in the plane. And let's see the spanning cycle, Hamilton cycle. Then what? If the drawing at no crossing, so in order to show that they are not planar graph, we have to show that no matter how you draw this, you must have a crossing. So assume it doesn't have a crossing. Then if C is drawn as a closed curve. So for example, in K5, no matter how it's drawn in, okay, there is no point of drawing it too complicated way. So it's drawn in this way. So this is closed curve. Then what? You have 5 chords in this K5. And we have to also draw these chords. The chords of the C, they must be drawn either inside or outside of this curve. So either you draw it inside or outside. Inside or outside. Inside or outside. And we say that the two chords conflict. Let's call it that the two chords conflict if their endpoints on this C occur in alternating order. So for example, this, and this appear in alternating order. So we say that this chord, this edge, and this edge conflict. And what we see is that when two chords conflict, we can only draw one of them inside. We can draw only one inside and one outside. If we draw one inside, then there is no way that you can draw the other one inside without crossing. So you have to draw it outside. Right? Then what? There are 5 chords. And without loss of generality, 3 of them must be drawn inside. I mean, it could be outside, but without loss of generality, it's inside. But then what happens? It's easy to check that then two of the three must probably of contradiction. Did it in K5. In K33, how do you know? You have to draw three chords. And inside, you can draw at most one chord. No matter which chord you draw, the other chords you cannot draw. Outside, you can draw one chord, the other chord you cannot draw, but there are three chords. So, again, this is contradiction by the same way. You can only draw one of them inside and one of them outside, but there are three chords. So, I will not write down the same similar sentence again. So, this proves that K5 and K33 are not planar. However, if you actually think about this proof again, it's not really mathematically rigorous. That once we draw this, we said that, inside and outside, what is actually, is inside and outside. So in this proof, we use the fact that a cycle partition the plane into two parts, inside and outside. And these parts are actually useful. Once we have some cycle, it's inside and outside. We want to treat this object. If inside, outside are useful concepts. And we want to actually give a name to this. And we want to treat them as one of the objects that we can deal with, and that would be very convenient. So, that motivates the definition of what's called basis. So, first, okay, we want to define what bases are, but first, let me recall what open set U in R2. And let me write it. On open set is a set U on the plane such that for any point in this open set, all points within, which is very close to P, some small distance from P all belong to U. And this is an open set. So for any point P, you take a very small open neighborhood of P, then that neighborhood must totally belong to you. Then this is 1%. Everybody here, I assume that they took mathematical analysis course, so you know what this is. Okay, then now we can actually define what are these inside and outside. We say a region is an open set U such that every 2 points in this region U lie on a curve in U. And the basis of a plane multigraph. The plane multigraph means that it's a multigraph with embedding given. These bases are the maximal regions, which is disjoint from the edges of the graph. Here, now again, edges are the curves that we have drawn in this plane graph. Sorry. And we say that the curve in the plane is closed if its first and the last points are the same point. And we say that this curve is simple. Let me give some colors here. Simple if it does not otherwise intersect with them. And with this definition, we can see some properties of this basis. So first, it's easy to see that every planar plane multigraph with triaxly many edges as one unbounded space. Why? I mean, if you have a finite graph and then the edges are all curved, and there are only finitely many edges, so there must be a large open set. You can take a large open set which contains all the edges. Then all the points outside, you can connect them by the edges. So all the points on this outside belong to the same maximal region. So that if you take the face containing one of these points, then there must be the unbounded space. And then that has to be the unique unbounded space. And also, we see that the 2 points, P and Q, which are not on the edges, are in the same phase if and only if there is a curve from P to Q that does not cross any edges, that crosses no edges. So this is also straightforward from the definition of the region and basis. And with this, we can state the theorem that's useful and then make our proof here more rigorous, which is Jordan curve theorem. A simple closed curve C partitions the plane into exactly 2 phases, and each of these phases having C as its boundary. Okay, this is Jordan curve theorem, but we don't want to prove this as this is a combinatorics course, and we only prove the following restricted Jordan curve theorem with the additional assumption that this curve is polygonal curve. What is the polygonal curve? Polygonal curve is the curve that's like locally linear. So that consists of the several segments, and each segment is like flat part of the line, and that's a polygonal curve. Simple closed polygonal curve might look this way. And then you have inside here and then outside here. So let's prove this restricted Jordan curve theorem. Of course, I mean, here, whenever we prove that certain embedding, we talk about embedding and drawing, it's not necessarily like the edges are not necessarily polygonal curve. It's more general curve. But I mean, knowing Jordan curve theorem is sufficient. And even if we just prove the restricted version, I hope it's giving you enough intuition and enough justification of the discussion that we will do later. So assume that C is given, simple closed polygonal curve. And what? It's a polygonal curve, so, and graph is finite. If C has finitely many segments. So any two non-intersecting segments on C cannot be arbitrarily closed. So we can choose certain epsilon so that the epsilon is smaller than any distance between two non-intersecting segments. So for example, this and this are intersecting segments, so we don't care about this distance, but between this and this, the distance is more than epsilon. And between this and this, the intersection is more than epsilon. This and this, the distance is more than epsilon, and this and this, the distance is more than epsilon, and so on. Then, what we can do, we have this then you difficult. And this closed curve, what we do is we take this one point on the C, and then we take points very close to this, but it's on the right side of the, so assuming that we are facing this way, we take one point which is on our right and very close. And what we do is we walk along the closed curve, then it points move together with us. So just as we follow it, see the very nearby point on our right fall right in the same place. So meaning that all points on here right on the same point, because we can connect two of them using some curve which is very close to this black edges, but it doesn't intersect the black edges, so all of them belong to the same face. And here, it's right, we can I mean, you can make it defined by dot product. You consider, you can give some orientation. So you just like, assuming you are following this curve in this way, the clockwise direction, or counterclockwise, you choose one of them. And then using the dot product, you can define what right means and left means. And same thing goes for the left side right. So point one here belongs to the same phase as well. And what do you know? Whatever point you take outside here, you take the shortest segment to C. So you take like some shortest segment, maybe let me use different color. Shortest segment to C from point not on C, it's arrived through one of these steps. So this arrived the blue part first and then hit C. From here, it hits the green part first and then hits C. So that means that you can find the curve. I mean, you can find the curve from this point to C, and then you stop it right before, then from this point to one of these blue points, so that it doesn't intersect with C. So, as every point not on C, writing the same phase with at least one of these two steps, which we have described. Okay, so we have now we show that there are at most two phases, and then we want to show that they are different phases. So to prove that they are different phases, we consider raising the plane. So for each a ray low from a point P, which is not on C, we define f of rho be the number of segments of C that rho intersect. So for example, if your C is this, and what you do is you take this P, and then say you have this row, a lay from this is half line that starts from here and then go indefinitely. And for this row, f of row is 3. 1, 2, 3. You it intersect 3 segments. Okay. Then what? Once you pick this P, if you change the direction, then you can check how this value of F low changes. It changes only when its low passes through an endpoint of a segment. So if you slightly alter, then wire this move to here, it doesn't hit any endpoint and it doesn't change. But once you hit it, it changes, and then afterwards, maybe let's draw this in a better way. Yeah, it may change because before, I mean, this segment was intersecting, but at the time it hits, it's intersecting two segments, and then moving slightly away, it's intersecting this one, but not here. This line here, it didn't intersect anything here, but now it's hitting this vertex. So it's intersecting with two, and then after that, it's still intersecting with two, right? So the value of F changes only at those points. Okay. But what we can see, what we can see is that the parity of this F low is the same for every row emanating from C, as long as it doesn't contain any vertices, endpoints of not vertices, endpoints of a segment of C. So this is polygonal curve. There are no vertices and no edges. I mean, it's endpoints of the segment. So I said it wrong. Why? So what patterns are possible? So when we have P, and one pattern is that this pattern could happen several times, but one pattern is that you have one segment on left and one segment on the right. Then when you move from here, and you move from here blue to green, the number of segments it intersecting is same. It doesn't change. At this moment, it's changes. So this is 1, this is 2, this is 1. But this one doesn't count because we consider the row which does not contain any endpoint. So we don't want to contain this endpoint. So this one doesn't count. I mean, it doesn't matter. And other possibility is that when we have this picture, so this one is 0 and this one is 2. And this one, again, it contains the endpoints we don't count. So this and this have the same parity. There are more complicated picture. For example, what if your P completely contains this segment? But still, for this, we don't care. It's actually 3, 1, 2, 3 segment is intersecting, but we don't care because it contains an endpoint. It actually contains the entire segment. But again, this is 1, this is 1. so it has the same parity. So we can actually check that this parity of F row is same for every row emanating from this specific point P, as long as this row does not contain any endpoint of the segment. And there are finitely many endpoints of the segment. So this is well defined. And this gives us a way to categorize the points depending on this parity. So this says that for given P, we can either say that this is even point or odd point, meaning that for this you consider all the row, which is, and as long as this row doesn't contain any endpoints, it gives the same parity. So it's either even point or odd point based on its value of F. And what do we know? For the points P and let's say X and Y. X and Y in the same phase of C, we can find the curve between them, which does not intersect with C. Moreover, we can find the polygonal curve. Some polygonal curve between them. Say this polygonal curve is P. It avoids C. And CS, so you have X and you have Y. Okay. CS the segment does not intersect C. Can check that the two endpoints of its segment are equal parity. Why? I mean, you have this is C, then for the 2 points here, you can take a ray emanating from here to here. And that ray has the same parity, and then that gives the parity of these two, as long as that ray does not intersect with C at the endpoints of some segment. If so, then we slightly alter, and you take this endpoint and this ray and then this ray, and then you make it as close as possible so that between them there are no endpoints of the C, then you can check that they have the same parity in terms of this number of intersections. So that shows that this and this have the equal parity, and this and this have equal parity, and this and this have equal parity. So X and Y have the same parity. Okay, but now what? It shows that all the points in the same phase have the same parity in terms of this F. But in a similar way, if you have C, then you take points X and Y. It is on the right and then on the left, which lies in this blue region and then green region. And then you can take a ray from 1 to here, ray passing through X and Y. Or maybe it's better to draw it this way. Then, if you take a ray from here to here, and then you take the ray from here to here, the F value differs by 1. Okay? we can actually choose this x and y so that the display does not intersect with C at any endpoints of the segment. Then that f value actually give you parity. So the endpoints of a short segment crossing C at opposite parity. As there are two distinct bases. First, we have shown that there are at most two bases, and then we show that the same base have the same parity in terms of which are defined by this. And then we show that there are 2 points with a different parity. So there are exactly 2 bases. Then they form the outside and inside base, which are one containing all these points in this green region, and then one contains all the points in this blue region. And because of that, the boundary, each of them has shared boundary. So, okay, so now we have defined the base. Okay, so in the next video, we will further learn about this base. So in plane graph, so far, the graphs are the ones which have 2 of the vertex and edges. But for plane graph, we now have bases as well. Now, in the next video, we want to investigate the relationship between these and then properties of this space. Okay, and I will see you in the next video.